Okay, in this video we'll do one more example of finding the null space and column space of a matrix. I have a matrix here A. It's a 4 by 4 matrix. I've row reduced it, and it row reduces to the 4 by 4 identity matrix. Pause the video and copy down the problem, and then we'll get started. Okay, the first thing we'll do is look at the null space. The null space is the set of solutions to AX equal to 0. And because I row reduced to the identity matrix, it has only the trivial solution. I can only put the vector 0 in there for x to make this equation true. There are no non-trivial solutions to that equation. That means the null space of my matrix is just the set containing the 0 vector. The dimension of that 0 space is 0. There is no basis. You'll never find a set of linearly independent vectors that spans that space, and we define the dimension of that space to be 0. And I hope that makes sense. A point is a zero-dimensional geometric object. A has a pivot in each of its rows. As a consequence, if I was to look at non-homogeneous equations like AX equal to B, that would be consistent for all vectors B in R4. As a result, that means every single vector B in R4 is a linear combination of the columns of A, and therefore every single vector in B, or every single vector B in R4 is in the column space of my matrix, or simply put, the column space of A is R4. As a result, the rank of the matrix is 4, the dimension of the column space is 4. There are 4 pivots in my matrix, which agrees with the rank. And we could have seen that from the rank theorem, which says the number of columns, which is 4, minus the dimension of the null space, which is 0, has to agree with 4. There were 4 there were 4 columns total. None of them were non-pivot columns. All of them have to be pivot columns as a result. There are many bases for the column space of A. I could take the actual columns of A, A1 through A4, these columns right here. They span, and they are linearly independent because there's a pivot in every one of those columns. Because the column space is R4 itself, it's somewhat of an unnatural choice. A better choice probably for a basis for R4 are the columns of the identity matrix, E1 through E4. And they both span the same space. They span the entirety of R4, and these both form a basis for the column space of A. Whichever one you prefer to work with is entirely up to you. Finally, if I look at the corresponding transformation from R4 to R4, given by matrix multiplication A times X, we see that the column space is R4. That's the range of the transformation, and therefore T is onto its codomain.